Okay, hello. So this week's video is another sort of inside the black box one, but it's a little different because it's not sort of saying how something that looks complicated and advanced is less complicated and advanced than you might think. Sort of is, but it's not exactly. But mostly it's just showing that there is a very useful concept in C++, we're in C++ again, that genuinely is quite complicated and quite advanced, but it's not so complicated and advanced that you can't get the idea of it. So this is an area of C++ templating which is called SFINAE. I think is quite often how it's pronounced. It's SFINAE, which stands for Substitution Failure is Not an Error. And essentially, the idea of this is that in C++, if you are templating things with certain restrictions, which is why this can get complicated, just the fact that when it tries to instantiate one template, it fails, that doesn't cause an error and doesn't stop the compiler from trying to compile your program. It'll keep looking for other things that can complete the template resolution. So let's just go back and show a bit first, right? So okay, so I'm going to want my IO stream, not Steam, stream library, because I always want that. So first of all, templates. These are something you're probably fairly familiar with in C++, but let's just show it to be clear. So I'm going to create a very simple function. I'm not going to demonstrate this SFINAE concept with functions, but this is the easiest thing. Okay. And I now create my main. And I call my function with an integer, double, and a string. And it compiles and it runs and it's able to print all three of those things, because essentially what the template is doing is it is substituting this T here, this type name, based on the type I actually call the function with. And this is the substitution. And it's also where substitution errors come in, because in these cases it's able to actually do the substitutions trivially. It's able to infer the type. If it can't infer the type, just to be absolutely clear, what I'd have to put in here is the type that I want. Which there is an int, there is a double, and here will probably be, yeah, it's not. Oh, right, because it's fixed length, of course. So if I make that now of the correct length, oh yes, an R value to an L value. Well, never mind. But the point is, those two work. Strings can be a bit of a pain in the neck to work out exactly what they template to, but that's it. Okay, so in this case, I am now explicitly telling this function what type it should replace this T here with. Okay, now, what you'd first think when you come across the idea is, okay, well, what about if I were to just create another function that can do things that only some things could do? You know, could I, for example, put in another template where I say call a function of whatever I'm passing in? And the answer, unfortunately, to that is no, because as far as C++ is concerned, all that I'm doing is I'm redefining my printer function. And this is one of the reasons why SFINAE is often seen as a fairly advanced thing, because a lot of the first and earliest things that you look at don't quite work because of the fact that the rules are actually quite complicated, and you do have to learn them, but the idea is pretty simple and very useful. So let's step back a bit here and show something that actually does work. Okay, so I'm going to create two classes, which I'm going to call A. In fact, I'll just create one to start with. That's the easiest way. Everything in this is public. And in it, I'm going to create a type. Okay. And then inside it, I'm going to have an instance of that type, which I'm going to call val, which is going to be L, lowercase l, let's say. Okay. That should be valid and compile. And it is, and it does nothing at the moment. Okay. But I have defined a type called type inside my class A, which is of type char. Okay. And I'm now going to create a template, exactly like I did, template function, exactly like I did before. It's going to take type name t, and I'm then going to create a function, which I'm going to call func1, which takes as its parameter, I have to put type name here as well. The rules for that are a bit messy, but never mind them. We're not talking the details here. So I'm now going to say of that type t, I want to get access to its type. And I'm going to print it again. That should have a value. Okay. So standard count, val, and a line break. Okay. I now create an instance of my A, and I now call func1. And I have now to explicitly put in the templating type, which is A, because it won't be able to infer it, because this parameter to the function doesn't directly use this type. Okay, and I'm then going to call that function with my A dot val. Okay. That compiles, and it runs, and it prints my L. That's fine. But now I'm going to create a class B. Okay, class B uses type, and it's not going to use type char, it's going to use a type int, and my val is now 42. Good Hitchhiker's Guide to the Galaxy reference. Okay, so I now have my A. After that, I will create my B, func1 of B, my B dot val. Okay. And it again compiles and again runs, and it prints both of them. Now, at the moment, all that I've done here is a very complicated way of doing what I had before. So I'm using a type stored as part of my class. I have an instance of that type in the class, and I have a function here that uses this type information from inside my classes to print a value. I have to pass a value in. It could be a completely different char in the case of the function templated on A. It could be a completely different int based on the type templated on B, but it would have to be a char or an int because it's my types A and B here that are determining what the type of the function is. Now, that actually has its uses in its own right. It allows you to use a class as a kind of way of indicating a type, holding type information, as well as other information. And that has its uses. But I'm now going to show where this comes together with SFINAE, because at the moment there is no substitution failure, because it's using the substitution in this one template here for both. I'm going to switch this type, and I'm going to call it type 2 in here. Okay, now, if I take out all this stuff calling func1 with B, that still compiles. Type 2 is a perfectly good name. But if I try and use func1, it's now going to fail to compile because there is no, so it tries to use this, but it goes, okay, there is no b : type because I've called it type 2. Substitution, template argument failed in substitution. So it's a substitution failure. So at the moment, substitution failure is an error because it's gone through every possible substitution and they've all failed. What I'm going to do now is I'm going to create a second function. And this second function I'm going to call func1 as well. But here, I'm not going to use t : type. I'm going to use t : type 2. And I'm going to put in a little string here, just hello world, in my print statement, so you can tell the difference between them. So the func is still called func1. Function is still function1 every time. But now it'll compile and it'll run, but it has selected a different function depending on whether I give it a class B or a class A here in this template information. So this is really the very simplest version of this SFINAE. This substitution failure is not an error idea. So essentially, when it's coming along and trying to produce a version of function1 for type A, it looks at this candidate here and goes, okay, yep, A has a type stored in it, which is a value type, and well, that's good. That works. I can look up that type, I can use it, the substitution succeeds, I can create my function. It comes along with B and it goes, no, there isn't a type inside B. This function, I can't make it. I don't have the information. There are rules on what is a SFINAE failure. And one of them is if a type is defined like this that doesn't exist. But then it comes to this version of the same template, and well, this type 2, that exists. I've defined that here, that works, and so it will now use this version of the function instead. But down here, when I'm calling the function, I don't know which of, I don't have to know. I just know that I'm doing it on A or I'm doing it based on B. And the compiler automatically selects a correct function for me here. And now it's selecting the thing not just on type, the way it would with a function overload, but on information about the inside of the type. And as it turns out, you can actually get an awful lot more sophisticated than this if you want to. So there is a generic thing which is called enable if, which is sort of a convenience function that makes a lot of this stuff a lot easier. Okay, so as always, when doing something live, something goes wrong, so I will start from here. So we're going to use enable if to demonstrate using SFINAE to produce a single function that can be called, or well, two functions that one or other is called depending on the type of the argument you call them with. Now that, of course, is normal function overloading, but here we're going to do it with templates. So you don't just have an integer and a double version. You can, for example, have what I'm going to do here, an integer version and a non-integer version. And it will just produce template for any integer type, and it will produce a template for any non-integer type, and they'll be different. And we do this by including a header, first of all, which is called type traits, which contains a lot of this useful stuff. And we're then going to use this enable if function. It is basically a function. So I will just create a templated function as before. Template type name T, if I could spell. There we go. And this function is going to have a return type that is given by this standard enable if function. Now, standard enable if is a function that acts during the templating thing, and it acts on types rather than acting on actual values, and it all happens during compilation. And the idea is you first of all use these triangular brackets again. This is just like I templated my functions explicitly. I'm templating standard enable if. And the first thing that I do is I give it something that's a condition that it can evaluate when the code is being compiled. So in this case, I'm going to give it standard is integral, which is a function that tests for whether something is an int. And I'm going to check that for t, and I'm going to check the value as a result of doing that check. Okay. Now I could optionally give another parameter here, something a type like int, but I'm not. So what this means is if this condition is true, then the result of this standard enable if will be a void. You know, not a void pointer, just void, like, you know, you do void for a function that doesn't return anything. If this value in here is false, it's typeless. And you can't have a typeless function. Functions may not return anything, void, but they can't just have nothing there. Constructors being a bit of an odd example that look like they don't, but constructors are special. But normal functions have to have a return type. And if this bit of standard enable if evaluates to false when the compiler gets to it, it won't return any type at all. Okay, so the function is going to take, once again, a value, and it's going to once again print it, because there's no point being imaginative when you're just demonstrating something. And I'm going to call this the integer path, print the value, and put in a new line. Okay, so there we go. Now I'm going to call this function with an integer. I'm going to check it compiles. Okay. And yes, here I did make a mistake, because standard enable if on its own returns something I don't want. I want to return the type that standard enable if gives me back, which is either a void or this typeless type. Unfortunately, it only gave me a warning. That's one of the weaknesses of doing a lot of these SFINAE things. You can get lots of unintelligible errors, but you can also get things which compile and just don't do what you expect. Right. Because it is a dependent scope. Okay, that is a weird thing of the templating system. Never mind that one too much. It's because while this does return a type, you have to make it absolutely clear to it that it is a type. So that has now compiled, and I can run it, and it prints integer path 10. At the moment, I haven't done anything very interesting. What's interesting is if I now create a different version of this. But now in this, I don't do is integral, I do not is integral. And I'm going to call this the non-integer path. Okay, so func 10, func 15L should give me a long. At the moment, both of those, even though one's an int and one's a long, use that integer path. But now, if I call this function with 105.6, which is a double, or with my hello world again, which is a string, it still compiles, and now it's selected the two different functions based on the type of the template. And this is very useful because function overloading is brilliant. It's one of the most useful features of C++, but it does have a substantial weakness in that you have to write out a function for every possible type, every overload you want. Whereas here, I haven't done that. I've just created two paths, one for integers and one for non-integers. And you can do much more sophisticated things. There are equivalents to this, is integral for things like, is this default constructible? i.e., does this object have a trivial constructor or not? Or all kinds of other questions you can want to ask. And you can use other elements of the templating system to create much more sophisticated approaches to this. It's too complicated to be worth showing here, but you can create things that detect, does this, does a class have a given class member, and things like that. Now that's sort of most of the classic substitution failure is not an error stuff. What I'm going to show now is one thing that isn't quite the classic SFINAE, but does much the same job. And I am also going to talk very briefly about something that is in the latest C++ standard. It obviously isn't terribly well used yet. The first thing I'm going to talk about is just using const expression ifs. So const expression if is an if that is a const expression. So const exp, constant expressions, are normally, you'd think of them in C++ as a function which, if it has to be evaluated when the code is running, is a function that is evaluated when the code's running. If it's not, if it's a function which a compiler can work out the answer to at compile time, it will do so. It will completely take out the branch. It'll work out if it's an if, or it's a function, it'll take out the function call. It'll take out any code, and it will just leave the relevant code with the actual answer in. And for ifs, that's quite useful because you still effectively have, I suppose it is still this SFINAE thing. You can test for things that are, not. You can include code that just isn't permissible in one branch of an if because it's literally never there. So I'm going to create another templated function. Okay. Now I don't do anything clever with the return type. Get in the value. Okay. I'm going to now do if. So I now put in my if const extra. So this means this if it possibly can be, will be evaluated when your code is compiled, not when it's running. And I'm going to put in exactly the same thing as I did with that SFINAE thing. And this is a lot more understandable, really. Okay, now I'm going to do is integral, because that's what I did before. So is integral t value. Okay, so that's just a Boolean value which will be true or false. And because of the way this works, this is part of the templating system. It'll be true or false when the code is compiled. It's true or false when it's run as well, but the compiler can work out which it is and and evaluate this if when it's compiling the code. And that's very useful because, so I'll just put in the same sort of thing again. So on integer path, value, new line. Other case, non-integer path, new. Okay, so, and I will, I should have left these in, but, func1, func hello world, right, and compile that. Okay, so it's warning me I have to use C++ 17, which is correct. This is a C++ 17 or newer feature. Okay, and I run it, and it selects the two paths based on that. As I say, the reason this is potentially very useful is because this if is evaluated at compile time, and the branch that doesn't exist, that isn't used, literally does not exist. I could in here put code that is valid only for integers. I could in here put code that is completely invalid for integers and would not successfully compile if called on an integer. But because this if is a constant expression if, the branch that isn't used simply isn't compiled in. So it's not there. It doesn't matter if it contains code which is invalid. So that's very, very useful. Okay, so that's it. Essentially, SFINAE, it's not easy to work with, but it is extremely powerful because it allows you to use the templating system to split things up, not based on this particular type, but based on properties that certain types have. And that's powerful when you just do it with things like integers versus non-integers, but of course it becomes extremely powerful when you start using it with the ability to deal with things about custom types. So next week we'll be back with something probably a little less abstruse, but hopefully this has been interesting.